Okay, section 4.2 is on the least squares regression line. And so the question we're going to answer in this section is, once we've established that there's a linear association between two variables, how can we describe that association? And it makes sense that since we're talking about a linear relationship, that an equation of the line would be the one that would help describe this relationship. So if you remember from algebra, the equation of the line was y equal mx plus b. That was the slope-intercept form. And m was your slope. So that gives you the steepness and the tilt of the line, if it's positive or negative, increasing or decreasing, and how steeply it's increasing or decreasing. And then b was where you had the y-intercept. And so that was where the graph crossed the y-axis. So in statistics, our least square regression line, we use slightly different notation. We're going to use y equal ax, or a plus bx. So slightly different. So our a is like the b in the algebra form, and our b in the statistics form is the slope. It's like the m. And x is what we call the explanatory variable. It's also the independent variable. And y is the outcome variable, or the dependent variable. And so in algebra, b is what we call the slope. In statistics, we'll talk about the interpretation of b, and we'll also talk about the interpretation of a. So let's do that now, and then we'll look at how this is used. So if you're interpreting a, which is our y-intercept, so it is the y-intercept. And sometimes A has no interpretation. If the data has both positive and negative x values, then A is the estimated outcome when the value of x is 0. There aren't that many situations where you're going to have both positive and negative x values. This is going to be the rarity. So if the x values are all positive or all negative, then A is meaningless. And that's going to be your answer most of the time. So if the x values are all positive, which is the most likely case, or all negative, which could happen, then the value of A is meaningless. It's still necessary to come up with the equation of the line, but it doesn't have any real-life interpretation. Okay, and then for interpreting B, now B is more important, it's the slope. For interpreting B, like I said, it's the slope. And if the values of the explanatory variable differ by an amount, so we'll say if the values of x, that's the explanatory variable, differ by an amount d, we're just going to denote it by d, but it'll be some number, then their predicted values will differ by the slope times d. then the Y values, we'll just say their predicted values. And we'll see this in some examples, will differ by B times D. Okay, and when we get this least squares regression line, how we write that, it's called the least squares regression line. And I'm not going to go into how it's found. If you read the textbook, you'll see why it's called the least squares regression line. It's also sometimes called just the regression line, or the linear regression line, more likely. It's also sometimes called the line of best fit. This book just refers to it as the least squares regression line. And it's y hat, and it's y hat because it's a sample value. It's not from the entire population. It's just a prediction. It's a guess. And it's a plus bx. And if you recall, when we were doing the calculating the value of r, part of that output, let me just switch to my calculator real quick. Part of that output, here's an r that we found earlier, part of that output includes a and b. And so you're going to find a and b the same way we found r. And that's just by going to stat, over to calc, and selecting number 8. Just like we were doing before. So let's look at a couple examples. So for the first one, this is the one that I think I still have in my calculator. We saw it in the last section. It's on government funding. It says the following table presents the budget in millions for selected organizations that received U.S. government funding for arts and culture in both 2006 and 2012. And we calculated the correlation coefficient in the last section. If you recall, it was R equals 0.995, which was a very strong positive linear association between the two variables. And we saw that if an organization was highly funded in 2006, it's also going to be highly funded in 2012. Okay, so for part A, they want us to compute the least squares regression line for predicting the 2012 budget from the 2006 budget. So in other words, they're wanting us to find y hat. And y hat, of course, is a plus bx. And so what you would do is you would go into stat, edit, and enter the data, which I already did. If you want to pause your video and do that yourself, we're looking at example 22 on page 173. But once you have the data entered, then it's like we were doing in the last section, stat calc number 8, and enter. And so there's the value of r we found earlier. And so our A is 11.710 and our B is 0.945. So we can see that our least squares regression line, y hat, will be a plus bx. So A was 11.710 plus B was 0.945. And I double check that. Yes, that was right, 0.945. 3 or 4 decimal places, we don't have a set rule here. So 0.945x. And so this is what we call our least squares regression line. And so the benefit of this is we can make predictions. So if we want to see, if we knew that a organization made a certain amount in 2006, then we want to predict what their funding is going to be for 2012, we could just plug that in for X. Okay, so for part B, it says if two institutions have budgets that differ by $10 million in 2006, by how much would you predict their budgets to differ in 2012? Okay, so we know that they differ by 10 million in 2006, so that's like our D is going to be 10. And how much do we predict their budgets to differ in 2012? Well, this is where we're going to take B times D. So my B was 0.945, and then we're going to multiply that by 10, which is how much they differed by in 2006. So if we multiply that, we're going to get 9.45, and that is in millions of dollars. So if the two budgets differed by 10 million in 2006, we expect them to differ by 9.45 million in 2012. Okay, and then for part C, predict the 2012 budget for an organization whose 2006 budget was 100 million. So X is 100. Now, to make this prediction, what we're going to do is we're just going to plug 100 in for X in our least squares regression line. So it's going to be 11.710 plus 0.945 times 100. But before I do this, I need to double check a couple things. First of all, to make our prediction, we really do need to have some sort of correlation, which we have a strong correlation here, linear correlation. Secondly, the number that we're plugging in has to be within the scope of the data. So we have to look at the 2006 budget because that's what X is. And we've got to make sure 100 fits within the range of values there. So in other words, we can't use this data that we have here and make some crazy prediction like, well, if they were getting $500 million, well, 500 is not too far out of it, like $1 billion per, for funding, what would the prediction be? Well, $1 billion doesn't fall anywhere within my scope. So I couldn't make that prediction. But like here, 100 is what we're predicting with. My lowest is 2, my highest is 460, so 100 falls within that range. So I can use it to make a prediction. So you're just literally going to type this into your calculator. We'll do 11.710 plus 0.945 times 100. And that is 106.21. So it's going to be $106.21 million is the predicted funding in 2012 for something that got funded at 100 million in 2006. All right, let's look at another one. We saw this one last class as well, or last section as well. It's on the carbon dioxide that is formed by new non-U.S. countries and U.S. countries in the years 1990 through 2006. And so we found a moderate correlation. Our R was negative 0.561. And so what we would do once we input this is we would go ahead and calculate A and B. Now I'm going to let you go ahead and do that yourself because there are no new keystrokes here. You're just going to clear out your list 1 and your list 2, input these values, and do stat calc number 8. And you'll see the same R that we got in the last section. And when you do that, you'll see that A is listed as 22.801. And B is listed, it's a negative correlation, it's negative 0.959. Okay, and so for the first question, compute the least squares regression line for predicting U.S. emissions from non-U.S. emissions. That's our y hat, and that's A plus BX. So that's going to be 22.801 minus, because it's a negative B, 0.959x. Don't forget that x. This is an equation of a line, so it's going to be y in terms of x. And so if the, whoops, I don't know why it does that when I scroll. If the U.S., sorry about this. Okay, if the U.S. emissions differ by 0.2 from one year to the next, by how much would you predict the U.S. emissions? The non-U.S. emissions differ by 0.2 from one year to the next. By how much would you predict the U.S. emissions to differ? Okay, so we're looking at that D being 0.2, and so we're going to take B times D. So your slope, which was negative 0.959, we're going to take that times D, which is 0.2. And that gives us, and it needs to be negative because we're expecting it to decrease because of the negative correlation. And we get negative 0.192 if we go to 3 decimal places. And so that's how much we would expect it to differ from in the U.S. emissions. And then finally, predict the U.S. emissions for a year when the non-U.S. emissions is 3.4. So X is 3.4, which if you go back and look at the data, that's a value that makes sense. And so we're going to get Y hat by plugging in 3.4 for X. So we'll have 22.801 minus 0.959 times 3.4. And so the predicted emissions are minus 0.959 times 3.4. So we get 19.540. And the units on this are metric tons of CO2. So that's our prediction for the U.S. emissions. And if you go back and look at the data, there were some places where it was actually 3.4. And you can see there was one right here. And another one right here. And you can see that we didn't exactly get the 19.54. It's just a prediction. You know, this is an exact value from the data, but we're predicting that it would be about 19.54 metric tons. Okay, I think I just have one last example on this. It's on butterfly wings, and it says, do larger butterflies live longer? The wingspan in millimeters and the lifespan in the adult state in days were measured for 22 species of butterfly. Following are the results. Okay, and what we're going to do with this one is we're going to compute the least squares regression line. We're going to decide if the wingspan, missed a question here. We're going to decide if it's possible to interpret the y-intercept. And then we're going to make some predictions. Okay, so the first thing you're going to need to do is enter this data. We've got 2 columns. Both of these columns you're going to put in for X for wingspan, and then both of these columns you're going to put in for Y for lifespan. So you should have 22 X's and 22 Y's. 22 X's in list 1, 22 Y's in list 2. I'm going to pause the video while I input the data as well. Okay, so now we have the data entered. So we're going to do stat and then over to calculate, and it's number 8 for the linear regression line. Enter. There it goes. So we don't have a real strong correlation. You can look at that, negative 0.412, but it is a weak negative correlation. So as the butterfly wingspan increases, it appears that the lifespan decreases. And then we can see the values of A and B there. So if we go back to the questions, they asked us to compute the least square regression line for predicting the lifespan from the wingspan. That's our y hat. And so that's going to go from A and B. So A turned out to be 52.043. And B, our slope, turned out to be negative 0.845. So our least squares regression line is 52.043 minus 0.845x. And is it possible to interpret the y-intercept? So they're asking about A. A is the y-intercept. And remember that only time the y-intercept has any meaning is if your x values are both positive and negative. And you can look here, all of my x values, it's not possible to have a negative wingspan. That doesn't make any sense. So is it possible to interpret the y-intercept? No. And this is because all the x values are positive. The only time it's possible to interpret A is when you have both positive and negative x values. Okay, then for part C, if the wingspans of two butterflies differ by 2 millimeters, by how much would you predict their lifespans to differ? So we're looking at D equal to 2, and this is where you take B times D. So my slope is negative 0.845, and we're going to take that times 2. And so we're going to get negative 1.69. And the lifespan is in days. So we would expect their lifespan to differ by 1.69 days if their wingspan differs by 2 millimeters. And then finally, for the last question, predict the lifespan for a butterfly whose wingspan is 28.5. So x is 28.5, and if you go back and look at all your x's, 28.5 is within the about range of the scope of my x's, so it makes sense to use our line to make a prediction. So y hat will be 52.043 minus 0.845 times 28.5. And this is going to be in days, is our lifespan prediction. So 52.043 minus 0.845 times 28.5, and we get 27, I'll just round to 3 decimal places, so 27.961 days is our predicted lifespan for a butterfly whose wingspan is 28.5 millimeters. All right, we just have one last section to look at on linear regression. Actually, we're also going to do a hypothesis test, so we actually have 2 more sections. But in the next section, the last one in chapter 3, we're going to find out the meaning of that r squared. Remember, in our output, that's the only thing we haven't talked about yet is r squared. And it does have a meaning and an interpretation, and we'll do that in the next section.